Okay, today we are going to discuss about Bohr-Somerfeld model of an atom. In previous class we discussed about Bohr model of atom. According to Niels Bohr, atoms are spherical in shape and mostly hollow. In atoms, at the center, that is at the center of the sphere, we have protons and neutrons. Around this spherical atom nucleus, electrons revolving in specified circular paths. As long as electrons are revolving around the nucleus in these specified circular paths, their energy is constant. So, Niels Bohr told that these specified circular paths of revolving electrons are called stationary orbits or main shells, which are denoted by KLMN and so on. These are also denoted by n equal to 1, n equal to, n equal 3 and so on. As we move far from the nucleus, the main shell size, this is first main shell, this is nucleus, this is first main shell, that is n equal to 1 shell, it is also called K shell, and this is second main shell, that is n equal to shell, that is L shell. As we move far from the nucleus, the size and energy, the size of first one is E1, second one is E2, stationary orbit, second stationary orbit size is E2. No doubt, according to Niels Bohr, E2 is greater than E1 and R2 is greater than R1. This is happened for next stationary orbits also. According to Niels Bohr, the electron which is present in lower energy state, if it is absorbs energy, it will goes to next higher energy levels. The electron which goes to higher energy levels, that is higher energy stationary orbits, are called excited electrons. The excited electrons are unstable, so they will lose their absorbed energy gradually to comes to their ground state. The absorption of energy by an electron or emission of energy by an electron will take place simple integer multiples of h nu, that is equal to h nu. This is also called quantization of energy. This quantization of energy reason is also not explained by Somerfeld. According to Somerfeld, angular momentum of electron is also quantized. That is, angular momentum of electron means what? Mass of the electron, velocity of the electron, radius of the rotating path of electron. The product of these three, m into v into r, is called angular momentum, is also simple integer multiples of h by 2 pi. Here h is Planck constant. All these things are discussed in previous class. previous class. Niels Bohr only explains the spectrum of species which have only one electron in them. Means Bohr could not give any explanation for the polyatomic species spectrum, and he could not give any account for the Zeeman effect and Stark effect. What is Zeeman effect? In presence of magnetic field, fine splitting of atomic spectral lines will be happened. The reason for the fine splitting of atomic spectral lines in magnetic field, which is called Zeeman effect, is not explained by Niels Bohr. For the drawbacks of Niels Bohr atomic model, Somerfeld come forward to explain the fine splitting of atomic spectral lines. He introduced elliptical orbits. Elliptical orbits. According to Somerfeld, each stationary orbit has, for example, k shell means n equal to 1. First stationary orbit has one stationary orbit. L shell means n equal to 2 has two substationary orbits. Means each stationary orbit has substationary orbits. The number of substationary orbits is equal to, for a stationary orbit, is its stationary orbit number only. That is, n equal to 1 stationary orbit has, that is k shell has one substationary orbit. N equal to 2, that is L shell has two substationary orbits. The substationary orbits are denoted by L letter. This L letter has some values which are depends on n values. N values gives information about stationary orbit. As n value increases, the size and energy of stationary orbit also increases. L values depends on n values, and L value starts with 0 and ends with n minus 1. That means substationary states or substationary orbits of a stationary orbit are denoted by L values. K shell has, K main shell has, that is first stationary orbit, n equal to 1 shell has only one substationary state. So it has only one L value, that is starts with 0, ends with n minus 1, that is 1 minus 1, 0. That is L has only one value, that is 0. So K shell has only one substationary orbit, that is L equal to 0 substationary orbit, and n equal to 2 has two substationary states, so it has two L values. L value starts with 0, ends with n minus 1, that is 2 minus 1, L equal to 1. So L values for n equal to 2 has L equal to 0 and L equal to 1. And the substationary states are denoted by L values. If L value is gradually decreasing, the elliptical shape of the substationary orbit becoming circular shape. For example, n equal to 2 has two substationary states. One is 100% elliptical in shape, another one is second one is 100% in circular in shape. L equal to 1 substationary state has 100% elliptical in shape. L equal to 0 has 100% spherical in shape. That means as L value decreases, that means L equal to 1 we are reaching L, from L equal to 1 to L equal to 0 means gradually L value is decreased. As decreased in the L value, the elliptical shape is gradually becoming spherical circular shape. And see one more example. For M shell, n equal 3 has 3 substationary orbits. So L values of n equal to 3 shell starts with 0, ends with n minus 1, that is 3 minus 1 means 2, L equal to 2. Between we have L equal to 1, 0, 1, 2. L equal to 0, L equal to 1, L equal to 2. We have 3 substationary orbits. These 3 substationary orbits are like this. For the stationary orbit M shell n equal to M shell n equal to 3, like this. Okay. So L equal to 2 substationary orbit of M shell, that is n equal 3, is 100% elliptical in shape. And next one is L equal to 1 is middle shape between circular and elliptical shape. That is L equal to 1 has neither 100% in circular shape nor 100% in elliptical shape. It is the middle shape or medium shape between circular and elliptical shape. Next, L equal 0 has 100% circular shape of n equal to 3, that is M shell. So here we conclude that elliptical shape has one long axis, another one is short axis. When L value decreases, this long axis size decreases, short axis size increases. When L value becomes 0, long axis and short axis size both will become equal to each other, then the elliptical shape will become 100% spherical, circular. So according to Somerfeld, each stationary orbit has substationary orbits. The substationary orbits are denoted by L values. L values depends on n values. So each stationary orbit with n value has L values. Those are starts with 0, ends with n minus 1. So for example, n equal to 1 has only one substationary state, that is L equal to 0. N equal to 2 has 2 substationary states, that is L equal to 0, L equal to 1. 2 minus 1, last value is for L is n minus 1. 2 minus 1 is L equal to 1. So like n equal 3 has 3 L values, L equal to 0, L equal to 1, L equal to 2, so and so on. This is about the concept of Somerfeld. which gives information about substationary orbits which are present in stationary orbits. Stationary orbits are denoted by n letter, small n, and substationary orbits are denoted by small l, which starts with 0, ends with n minus 1. That is nothing but l values or depends on n values. First stationary orbit has only one substationary orbit, second has two substationary orbits, and third stationary orbit has 3 substationary orbits, and so on. This is about Somerfeld model. Next, we should discuss about quantum numbers. Quantum numbers are of 4 types. One is principal quantum number, second one is azimuthal quantum number, third one is magnetic quantum number, spin quantum numbers. These quantum numbers will give information about an electron which is present in an atom. First, we should discuss about principal quantum number. Principal quantum number is proposed by Niels Bohr, which is denoted by small n. According to Niels Bohr, principal quantum number, as n value increases, the stationary orbit size and energy both will be increased. That means this is the first stationary orbit, this is the second stationary orbit. N equal to 1 is first stationary for first stationary orbit the principal quantum number is n equal to, and the n equal to is the principal quantum number of second stationary orbit, and so on. As we move far from the nucleus, n value is increasing and stationary orbit size and energy also increasing. That means principal quantum number tells about the energy and size of the stationary orbit. That is, as n value increases, the energy and size both will be increased. The number of maximum electrons present in a main shell or stationary orbit with n value, principal quantum number n, is equal to 2n square. That is, in n equal to 1 main shell, that is K shell has 2 electrons. In n equal to, that is L shell, has 2 into 2 square, 8 electrons, and so on. So the maximum number of electrons present in a stationary orbit with the principal quantum number n is equal to 2n square. Next one is azimuthal quantum number. Azimuthal quantum number is also called angular momentum quantum number, which is denoted by small l. These azimuthal quantum number L values depends on principal quantum number values, starts with 0, ends with n minus 1. That means L values, angular momentum quantum number values, starts with 0, ends with n minus 1. Means L values, azimuthal quantum number values, depends on principal quantum number values. Why? Because already according to Somerfeld we can conclude that each stationary orbit has substationary orbit. That means L values giving information about substationary orbits. For example, n equal to 1 has one substationary state. n equal to 1 has one substationary state. N equal to 1 has only one substationary state and its value is 0. Already I have explained this concept, that is azimuthal quantum number concept, in Somerfeld model only. Once again I am repeating. If n equal to 1, that is first stationary orbit, so the azimuthal quantum number values starts with 0, ends with n minus 1. That is, starts with 0, ends with n minus 1 means 1 minus 1, that is 0. So n equal to 1 has only one stationary orbit according to Somerfeld, that is with L equal to 0 azimuthal quantum number, which is proposed by Somerfeld only. N equal to 2 has two substationary states. Those are L equal to 0 substationary state, L equal to 1 substationary state. Okay, that's it. Next. And n equal to 1 substationary state, L equal to 0 is called 1s substationary state. N equal to 2 has two substationary states, L equal to 0 and L equal to 1. Those are namely 2s substationary state and 2p substationary states. Like this also happened in case of n equal to 3 and n equal to 4 also, and so on. So this is about azimuthal quantum number. Next we discuss about magnetic quantum number. Magnetic quantum number is denoted by ml. These magnetic quantum number ml values depends on azimuthal quantum number L values. This ml value is introduced by Lande. The ml values gives information about the orientation of orbitals present in substationary states, which are degenerate. Means degenerate orbitals are of almost equal energy. Degenerate orbitals have almost equal energy. For example, n equal to 1 has only one substationary state, that is 1s. It has only one orbital, that is 1s orbital only. This is only stationary substationary orbit and it is only orbital. N equal to 2 has two substationary states, L equal 0, that is 2s substationary state, L equal to 1, 2p substationary state. According to magnetic quantum number, each substationary state has degenerate orbitals. S substationary state has whatever it may be, it is 1s or 2s or 100s orbital. It has only one orbital, that is s orbital only. P substationary state has 3 orbitals, namely px, py, pz. Means the ml values gives information about degenerate orbitals present in substationary orbit. These ml values depends on L value, that is angular momentum quantum number value. ML values starts with minus L, ends with plus L, between we have 0. Total ml values are equal to 2L plus 1. 2L plus 1. For example, for n equal to L equal to 0, s orbital means L equal to 0. P orbital, P subshell means, or substation, L equal to 1. L equal to 1, P subshell has ml values 2L plus 1 means 2 into L equal to 1. L equal to 1. L equal to 1 for P subshell. So ml values of P subshell are equal to 2L plus 1. L equal to 1 means 2 into 1 plus 1. How many? 3. By that reason only I told you for P subshell we have 3 degenerate orbitals which have almost equal energy, namely those are Px, Py, Pz. For example, L equal to 2 subshell means that is D subshell. It is denoted by D subshell. D subshell. D subshell has 5 degenerate orbitals: dxy, dyz, dzx, dx square, y square, and dz square. Why I am telling for D subshell, that is L equal to 2 quantum number, which is azimuthal quantum number, has 5 degenerate orbitals, means according to the formula 2L plus 1, 2 into 2 plus 1, 5. So 5 degenerate orbitals are there. So, and each orbital consists only 2 electrons in maximum number. So azimuthal magnetic quantum number gives information about the orientation of the orbitals around the nucleus. Each orbital contains maximum 2 electrons in each. Okay. Next, spin quantum number. Spin quantum number gives information about the rotation of electron around the nucleus in an atom. If an electron rotates around the nucleus in clockwise direction, that is called plus of spin. This is anti-clockwise direction, so it is minus of spin. If any electron rotates in clockwise direction around the nucleus, so its spin is called plus of spin. Clockwise spin is called plus of spin, anti-clockwise spin is called minus of spin. So simply the spin quantum number gives information about the electron around the nucleus, either it is in clockwise or anti-clockwise. If it is in clockwise direction rotation, the electron spin is called plus of spin, otherwise it is called minus of spin. The spin quantum number is introduced by Uhlenbeck and Goudsmit in 1925. These quantum numbers are very useful for the placing of an electron in an atom in an appropriate manner. Placing of electrons in an atom in the stationary orbits is called electron configuration. We are placing electrons in stationary orbits means each stationary orbit has substationary orbits. Substationary orbits have degenerate orbitals in them. So we are filling electrons of an atom in stationary orbits means we are filling them in orbitals in an appropriate way. What is the appropriate way to fill the electrons in orbitals is told by three principles. Three principles. Those principles will be studied in next class. Once again, I am repeating that principal quantum number tells about energy and size of the stationary orbit, and azimuthal quantum number or angular momentum quantum number L gives information about the substationary orbits present in the stationary orbit. N equal to 1 stationary orbit has only one substationary orbits. It has the value L equal to 0. Why? Because L value starts with 0, ends with n minus 1. L equal to 0 means that is 1s orbital, and so on. Okay, this is about quantum numbers. We will discuss about the principles which are involved in the writing of an electron configuration of an atom in later classes. Here I am giving you a clarity that I am teaching you and giving information about the atomic structures in basic concepts only, which is useful for the beginners. I will start my sessions in later classes for the IIT and NEET exams purposes. So please follow my channel, subscribe my channel, and watch my videos. If you like my videos, please share them and give me a boost for the uploading many more videos with better quality present to the present situation. In lockdown period, I am trying to give you with the scope which I have with me in this time. So please cooperate with me. Thanks to one and all.